All right, good morning. I think it's time to start. Today, in the first part, I'm going to show you how to derive the equation, generic equation. Okay, right now we are in chapter 3. The concept of chapter 3 is to develop a set of equations so that we don't have to set up a shell balance anymore. That equation is supposed to be generic enough so that we can use it for any kind of system. Okay? So in the first part, I'm going to show you how to do the derivation for the mass balance only. And then we will give you the equation for momentum balance. And at the end, I'm going to give you the examples how to use that equation to solve the problems. Okay? And let's start. As I said, what we learned from chapter 2 depends on the shape of the shell. And shape of the shell, if you got it incorrectly, you end up with either problem very difficult to solve an equation or incorrect answer. Okay? So the idea is to shrink down the shell into the most generic form. If your system is rectangular, if it seems to be rectangular, so rectangular coordinate would be proper choice to do the shell balance, right? And the most generic form of shell in rectangular coordinate would be a cube or a box with the length of delta x, delta y, delta z. So if you take a shell balance around this box, you have to end up integrating in 3 dimensions, integrating with respect to x. That means you extend this shell to cover x direction, extend it in y direction and z direction as well. Okay? So the equation that we will develop would start from this kind of shell. And if in general there's a velocity or there's a fluid flowing into a box in generic direction, and this vector has a velocity v. Of course, you can expand this v into 3 components, vx, vy, vz, right? If we do that, then we can say that I can move vx, vy, and vz out from this expansion and translate Vx here. Vx is translated here, going into the x direction. Vy is going in y direction, and Vz is going in z direction. Okay? So basically, I expand this component, the component of this vector, and move them so that each component would enter the box in the perpendicular direction. So Vx would enter this face, this area. Vy would enter the front area, and so on. Okay? Then, if I want to do the mass balance, the generic equation for mass balance is mass going in subtracted by mass going out, equal to accumulation of mass within a box. Okay? Remember, the unit of all terms supposed to be kilogram per second. It's supposed to be rate of mass. Right? So mass going in, that's supposed to be mass flux multiplied by the cross-section area, or the area perpendicular to the flux. Okay? Let's start. We have mass enter the box in three directions. In x direction, you have Vx. Okay? If you take a look at the unit, Vx should have unit of meter per second. In order to convert this Vx into the mass flux, you want mass, right? So you need mass here. And you want flux. Flux is supposed to be mass per square meter per second. So in order to get square meters down here, we need to divide by cube, meter cube, so that it cancels one direction here. You end up with kilogram per second meter square, right? This is kilogram per cubic meter. That's density. Okay? So if you take Vx, multiply by density, this Vx supposed to be direction in x direction, or distance in x direction, multiplied by kilogram per cubic volume here, cubic meter, volume. The volume is the whole box. If you multiply by direction in x direction, what you have should be the area highlighted here, right? If you cancel this, you get meter square. This meter square is supposed to be area perpendicular to the direction of the V. Okay? So the whole thing here becomes mass flux. If you multiply the mass flux, this is mass flux, multiplied by the area perpendicular to the flux, which is this area. The area highlighted here is supposed to be delta Y, delta Z. Okay? Just like doing shell balance, you take the flux, multiply by the area perpendicular to the flux. This is input, so it takes place as X minus by output, delta Y, delta Z, rho Vx taking place at X plus delta X. This will be in minus out in X direction. Same thing for Y direction. Flux in Y direction going this way, so the area perpendicular to the flux is supposed to be front area here with the area delta X, delta Z. Okay? The flux itself is rho Vy entering at Y. Going out, same surface, but different location. This is Y plus delta Y. Lastly, in Z direction, that will be delta X, delta Y, rho Vz at Z minus delta X, delta Y, rho Vz at Z plus delta Z. So that's in minus out in three directions. Okay? These two terms has been taken care of. Accumulation is rate of change of mass within the box. So it's supposed to have unit of kilogram per second. Okay? Mass within the box can be calculated based on volume multiplied by density. Okay? So if I have volume in cubic meter multiplied by density, kilogram per cubic meter, this is volume, this is density, you get kilogram. But at the end, you need time. How do we put time over here? Accumulation term describes rate of change. Okay, it's a change of mass within the box. So basically, change is a change with respect to time. Accumulation term always be the term with respect to time. So this term is basically volume, delta X, delta Y, delta Z, times density that is changing with respect to time. Changing with respect to time is differentiation with respect to time. Okay? The volume itself will be fixed. We do not change the volume of the shell. You can move this one in here and you set the change of the total mass with respect to time and take the volume out. That will be the same. All right? So this first line that's in and out in x direction, y direction, z direction, if you divide the whole equation by the volume, if you divide by delta x, delta y, delta z, this term would disappear from the right-hand side. this term would disappear, and you end up with delta x as a denominator. If you divide it by delta x, delta y, delta z, this term would be gone. And you have this term divided by delta y. And at the bottom, you have division by delta z. Okay? And then, similar to what we did in momentum balance, we are going to take limit delta x, delta y, delta z approaching 0. Limit of delta x approaching 0, the first term turns to be negative of differentiation with respect to x of rho vx. Let me put this term first. This term will be d rho by dt equal to this term. That would be minus d by dx rho vx. And then minus d by dy of rho vy. Right? This term, if you take limit delta y approaching 0, it turns to be differentiation with respect to y. And last term, you end up with d by dz of rho vz. Okay? So if I take minus sign out, if I take it out, this would be positive. Okay? Then, according to what we discussed from the very first class, differentiation with respect to x, y, and z of the component in x, y, and z, that's del. Okay? By definition, this is del dot whatever inside differentiation is a del dot rho v. Okay, and we have negative up front. So the equation turns to be this one, and this one is represented by vector v. All right? This equation is called equation of continuity. In general, it is mass balance for the system. Okay, any question? Now, from the equation of continuity, oh, by the way, this equation of continuity, this is supposed to be general. That means it is applicable always. Okay, this is a mass balance. Whether you do it in any kind of system, this is still correct. So if you write this equation down, that means you are doing mass balance. For special case, if your fluid is incompressible, what does it mean, incompressible fluid? Doesn't matter what you do, the density will not change, right? So incompressible fluid means density is constant. And again, I would like to emphasize that the word constant in transport phenomena means a lot. It's constant with respect to time. It is also constant with respect to position. So that doesn't change with respect to time and position. So that means differentiation with respect to time here turns to be 0, right? So for incompressible fluid, d rho by dt will be 0. At the same time, if you go back to the top equation, density does not change with respect to position, means that you can move this out of the differentiation. Okay? You can move this row out, this row and this row moving out as well. In other words, that means you can take this row out of this del. Okay? So it means that del dot rho v would equal to rho times del dot v. This is left-hand side of the equation of continuity. This is right-hand side. If you take them together, you end up with del dot v equal to 0 for incompressible fluid. Okay? So remember when we did the problems, I said every time you have liquid, we will assume to be incompressible fluid, and then del dot v will be 0. This is the proof. All right? So you can say it, if your system is fluid, which is liquid, liquid can usually be assumed to be incompressible, and therefore you can write equation like this to represent equation of continuity right away. Okay? Now, if I change the coordinate from rectangular to cylindrical, do we need to draw the new shell, develop the equation again? Now the trick is, although this equation, the top equation, is written in rectangular coordinate, if you can convert this equation to this equation, it is vector. Now when it is vector, you can re-expand it in cylindrical coordinate right away. Okay? So starting from this equation, if I write it down for cylindrical coordinate, I will end up with d rho by dt equal to on the right-hand side, that will be negative. Inside this term, if you write it for cylindrical coordinate, you get 1 over r d by dr rho r vr plus 1 over r d by d theta rho v theta plus d by dz rho vz. Okay? So this equation was obtained not by doing balance again, but it was obtained from this generic equation that is written in terms of vector together with the knowledge of vector, that this operator in cylindrical coordinate can be expanded to this form. All right? So when we do derivation, we will do it easy way on the rectangular coordinate, try to convert it into vector form so that we can re-expand to any coordinate. So we do not have to do balance for all coordinates. Understand? You don't have to do re-expansion by yourself. These equations are listed and will be given in examination room. So all you have to do is picking the right equation for the right coordinate. Okay? Now, from mass balance, if I want to do momentum balance, now suppose the flow going in and out of the box, the same box, okay? And the flow can be expanded into 3 dimensions. There will be Vx, Vy, and Vz. Okay? So now they will have x momentum, y momentum, and z momentum entering this box at the same time. X momentum should have 3 components associated with it. X momentum is supposed to have phi xx, there will be phi xx, phi yx, phi zx. These 3 would have second subscript to be x, so they are associated with x momentum. Okay? The first one is x momentum transferring in x direction. So I can write down transfer direction like this. So this would be phi xx. Second one is x momentum transferring in y direction. So it goes this way. This is phi yx. Third, phi zx should enter along z direction. So this is zx. Right? This is for x momentum. For y momentum, you have xy, yy, zy. Okay? xy is x momentum transferring in x direction. So xy should be transferred here, going in x direction. Double arrow represents the direction of transfer. Okay? Yy, that's y momentum transferring in y direction. It will go here. And zy would be here. So for z momentum, you have xz, yz, and zz. Okay? So if you do the balance for these momentum, at the end, the derivation is a little bit lengthy. It's quite long. So I do not want to show you here in class. If you're interested in this kind of derivation, they are in the textbook. Okay? And maybe I do some video so that show you the derivation of all this. But at the end, what we have to do is doing the balance. But because these momentum are very complicated, so instead of doing balance for all directions at the same time, we will try to split, doing balance of each momentum separately. So if I do the momentum, x momentum balance, I will pick this one, and this one, and do the balance first. If I do that, I will end up with x momentum balance you get something like this. Okay, the form of equation would be similar to what we derive for mass balance. This is accumulation of momentum, accumulation of x momentum within the system, in and out. Momentum, you need to add one more term, which is generation of momentum. It can be generated by external force. So external force is gravity. Okay, so if you do x momentum balance, you get this equation. If you do y momentum balance, you get similar equation. Just change this one into xy, yy, zy, and so on. All right? So you have equation for y momentum and z momentum as well. 3 equations. If you combine these 3 equations into one single equation, for instance, for y component, you end up with something like this. Okay? So if I want to combine these 3 together, I can say that all 3 terms can be combined into d by dt of rho v. Okay? V itself has 3 components. If you multiply by rho and take differentiation, it still has 3 components. Their component would be this, this, and that. Okay? On the right-hand side, if you combine it, you end up with something like this. Okay? Same thing here, rho gx, gy, gz. Combine, you get rho and vector g. At the middle, now we have 9 terms. It turns to be tensor, and by definition, it is del dot tensor. Whenever you have dot products, the direction is reduced. When you have vector dotted by vector, you end up with scalar. The result has one less direction. So if you have tensor, which has 2 directions, dotted, now the result would have one less direction, turns to be vector. So the whole term here is a vector. Okay? Now if I turn phi, that's a combined flux. Combined flux is consisted of convective flux, molecular flux, and pressure term. But pressure would appear only in normal direction. So you multiply by this delta. The delta by itself is a tensor of something like this. It has 1 in normal direction, so when you multiply by scalar pressure, you end up with pressure only in normal direction. Okay? Now, the rest is a little bit complicated. Basically, I put this in here and then move this part together with that part, okay? And you see that this is differentiation with respect to time, added by something, del dot velocity. So it can be manipulated or can be converted in terms of substantial derivative. On the class on Tuesday, we talked about 3 kinds of differentiation: partial differentiation, total differentiation, and the last one is called substantial derivative. Okay? Substantial derivative tells you the change with respect to observer traveling at the same speed as the flow. Okay? Now the point is, when you plug this in here, move the convective part to the left-hand side, do some manipulation. At the end, you end up with equation like this. All right, and this is supposed to be highlight. Anything highlight is supposed to be very important. This equation is called equation of motion. Basically, it is momentum balance. If you look at the equation itself, the whole equation is vector. Unlike equation of continuity or mass balance, the whole equation of mass balance is scalar. Okay? For mass balance, earlier we have d rho by dt equal to minus del dot rho v. Okay? This is equation of continuity or mass balance. If you look at mass balance, you should see that this term is scalar. Rho is scalar. Differentiation of rho is supposed to be scalar. Okay? V is vector. Multiplied by scalar is still a vector. Vector dotted by another vector. The whole term here is a scalar. So this equation is scalar equation, even though there's a vector inside. Equation of motion, on the other hand, is a vector. The whole equation is vector. For instance, this is vector. V is vector. You differentiate it, you get vector. Multiply by scalar, this term is a vector. Okay? Rho g is obvious. You have vector multiplied by scalar, you get vector. Tau is tensor. You have two directions. Dotted with another vector, direction is reduced. Then the whole term here is a vector. This is vector operator. Del is vector. Operated on scalar, you still get vector. So the whole term, the whole equation actually can be split into three sub-equations. Okay? So whenever you pick this equation, essentially you have to write three equations in each direction. Now, in similar manner, if I replace tau with Newton's law, under Newton's law, it means viscosity is constant. Okay? Basic assumption of Newton's law is that viscosity is constant. If I also add another assumption that density is also constant, in that case, you end up with another equation All right. This equation, again, supposed to be highlighted. It is very, very important. It has a name, Navier-Stokes Equation. People have listed 10 most important equations of all time, of the history, okay? You know, one of them is Newton's law, F equal to ma. There's Pythagoras, okay? There's Einstein, E equal to mc squared. One of them, one of the 10, is this equation, Navier-Stokes equation. So essentially, Navier-Stokes equation is momentum balance under assumption of constant density and constant viscosity. So if you are working with liquid, liquid can be assumed to be incompressible fluid, which has constant density, right? If your liquid is Newtonian liquid means viscosity is constant, then you can use this equation right away. The good thing about this equation is that inside here, you have velocity, which is measurable. In the equation of motion, you have tau, which cannot be measured. So this is more convenient. Any question? Now we have 45 minutes. Let me give you example how to use equation. By the way, in the same manner, this equation is written in form of vector. So therefore, even though it was derived based on rectangular coordinate, if you know how to expand this vector into any cylindrical or spherical coordinate, you can do that without re-derive the whole thing. All right. Example would be what we did in chapter 2, flow of liquid in the inclined plane. The very first example that we did. Okay. Now we want to solve this equation using what we learned in chapter 3. Basically, we want to use generic equation. The way we do it, same thing. You set up the picture of your system. You assign direction, assign axis, okay? I'm going to assign in the same manner as what we did. Secondly, you have to identify velocity component, Vx, Vy, Vz. We did already, and we found that Vx equal to 0, Vy is equal to 0, and Vz is a function of x only. Okay? Now, in general, you can start with any equation. But in the first part here, in momentum session, I will suggest you to start with equation of continuity. All right? If we move on to energy part or mass part, maybe we can start with something else. But in this session of momentum balance, I would suggest you to start with equation of continuity, okay? So as long as your system is single species running under isothermal condition, no temperature change, one single species, no reaction, you should start by doing mass balance, okay? So if I start with equation of continuity, basically d rho by dt plus del dot rho v equal to 0. This is generic form of equation of continuity. Under assumption, you have to assume constant density. Because it is water, we will assume it to be incompressible. We will assume the liquid to have constant viscosity or being Newtonian fluid. Under assumption of constant density, this term is 0. This term can be moved out of differentiation. At the end, you end up with del dot v equal to 0. Okay? If you expand this product, del product, you get differentiation with respect to all axes of v component, dvx, dvy, dvz, with respect to x, y, and z respectively, equal to 0. Once again, you don't have to remember how to expand it. The equation will be given. Okay? Then, if you do assign all these velocity components, plug it back into the equation, you see that Vx is 0, Vy is 0, Vz is not 0. So by the equation itself, you end up with dVz by dz equal to 0. This is what you will get from equation. In other words, from this equation, you end up with the fact that Vz is not function of z. Right? If it is function of z, differentiation will not be 0. If it is not function of z, when you differentiate it, you take it as a constant. So this would give you conclusion that Vc is not function of z. You don't have to analyze the problem. This equation will give it to you. All right? Now, that's the second part. We start with Navier-Stokes equation, because we assume constant density and constant viscosity. All right? So you need a moment to write the equation with me. Or you can wait until I finish and take a snapshot. In Navier-Stokes equation, there are three components. The equation itself is a vector, so it can be split into three components, x, y, and z component. Okay, meaning x momentum balance, y momentum balance, and z momentum balance. Now, this is the reason why I cannot use projector or PowerPoint. Equation is too long. It's very easy nowadays. Just take a picture. Right? In my time, I have to write down everything along with my professor. Oh, by the way, all these equations are already on Courseville. You can just basically download it. It will be much easier and look prettier than my handwriting. Okay? So by equation, you have x momentum balance, y momentum balance, z momentum balance. Okay? The first term on the left-hand side is basically substantial derivative. This is pressure gradient. And then this term would be del square or Laplacian of V and rho g. Okay? This term within the mu basically is a molecular transport. It was converted using Newton's law. So this term, the whole term here, is basically molecular transport added by pressure and external force. Okay? So in the left-hand side, that's an accumulation term added by convective transport. Now, how to do it? Very easy. Just follow. First, we know that, just write it here. Vx is 0, Vy is 0, Vz is not function of z. Okay? Vz is a function of x. This one we got from equation of continuity. Okay? So keep it up. Vx is 0. X is 0 here. 0, 0. Okay? Vx is 0, 0, 0. There's no gravity in x direction. Oh, there is actually. Gravity would be g sine beta. If I redraw the picture, this is the flow. So we have g. This is beta. So if you expand this g, now you have g sine beta and g cosine beta. Okay? In x direction, this is x direction, this is z direction. X direction, gx is g sine beta. Okay? So from here, if I move this pressure to the left-hand side, I end up with dp by dx equal to rho g sine beta. If you remember, when I did this problem using shell balance, I show you x momentum balance as well. And at the end, we end up with the same thing. Okay? For y component, Vy is 0, 0, 0, 0. 0 here, 0 here, 0 there. I always love to say that there are a lot of 0 in transport phenomena. A lot of 0. Yeah, in the examination paper as well, there's a lot of 0, 0, 0, 0. Okay? Gy, in y direction, there's no gravity. Gy is 0. So in this case, you end up with dp by dy equal to 0. In other words, it means that pressure is not function of y anymore. There's no change in pressure with respect to y. For z component, Vc is not 0, but the whole term here can be taken to be 0 under steady state assumption. Okay? Under steady state assumption, there's no change with respect to time. Vx here is 0, Vy is 0, Vz is not 0, but the whole term here was found from equation of continuity that it is 0. Also, you can say that Vz is not function of z, so differentiation with respect to z would give you 0. Okay? Vz now is function of x, so that means definitely this term must be kept. Vz is not function of y, the whole term here turns to be 0. If it is not function of y, you take first derivative, it's 0. You take second derivative, it is 0 still. Like this. dv by dz, dvz by dz is 0. If you take another differentiation with respect to z, it's still 0. Okay? And gravity in z direction is g cosine beta. Okay? Now, in this case, you have to analyze further that our pressure does not change with respect to z. Remember when we said pressure on the surface is atmospheric. Pressure down here is supposed to be atmospheric added by something. Here, pressure is also atmospheric. If you add the same depth, these two pressures would be the same. So that means pressure does not change with respect to z. So if it's not function of z, this term will be gone. Then what I have left, if I move this to the left-hand side, I will get minus mu dv squared. I can change this one to total differentiation because my Vz is a function of x only, equal to rho g sine beta. All right? And this equation is exactly the same as what we got from doing shell balance. So for someone, they would normally prefer this way because you don't have to worry about setting up shell anymore. Basically, you just eliminate terms that are 0. In this particular example, it's quite straightforward. But on the other side of the equation, if you are not quite certain on this part, then your life is hell. See how long the equation? If you cannot eliminate terms that are 0, if you're not sure whether this term should be kept or not, and you keep it, then you need high skill in math. All right? Any question? Okay, I give you a couple minutes just to make sure you understand everything. Write it down. Oh, I'm sorry. Cosine beta, yes, thank you. Okay? Can I erase it now? Now, if you do not want to take a snapshot, could you go into the course view, download Appendix B, and find the Navier-Stokes equation for cylindrical coordinate. All right, what we want to do is repeat the calculation in this example, flow through annulus. Okay? And when we were in chapter 2, we analyzed this already. The flow is going upward. We got VR equal to 0, V theta is 0, Vz is a function of R only. Okay? So if you set up equation of continuity, again, under assumption of incompressible fluid, you should get del dot V equal to 0, right? And now if you expand this in cylindrical coordinate, you end up with 1 over R d by dr, rvr, plus 1 over r d by d theta of v theta, and dvz by dz equal to 0. So if you take VR here to be 0, VR is 0, V theta is 0. What you get from here is this part, Vz by dz is 0. In other words, Vz is no longer a function of z. It's not a function of z. Differentiation gives you 0. Okay? So if you get dvz by dz equal to 0 from equation of continuity. Once you get continuity done, set up equation of motion or Navier-Stokes equation. All right? So give me a couple minutes just to write it down. Of course, there's R component. Okay, if you want to write it down yourself, take a couple minutes to finish. Or you can take a snapshot, or you can download the equation from Coursefil. Are you ready? Ready? Okay. Now, first component, VR. VR is 0, so 0 here, 0 there, 0, 0. We set as 0, this term will be 0. Okay? VR is 0, 0, 0. We set as 0. And there's no gravity in R direction. So basically, you end up with dP by dR equal to 0. In other words, pressure is not function of R. Okay? For theta, everywhere you have V theta, it is 0. So V theta here is 0, 0, 0, VR 0, no gravity in zeta direction, it is 0. So again, you end up with pressure is not function of theta, or dP by d theta equal to 0. So pressure is not function of theta. All the energy writing that equation would be thrown away quickly. Okay? The last one is important because we know that the flow is in z direction, so therefore there will be z momentum. So this equation, which is z momentum balance, should not be 0. All right? So I go slowly. First term, Vz is not 0, but under steady state assumption, the whole term does not change with respect to time. It turns to be 0. Vr here is 0. V theta here is 0. Vz is not 0. However, this whole term is 0 according to equation of continuity. Okay? Pressure is changing with respect to z. This term must be kept. So I will highlight with blue ink. This should be kept. Vz is function of r. It's changing with respect to r, making the whole term here to be non-zero. This term must be kept as well. Vz is not function of r. So differentiation with respect to r should give you something. Okay? Vz, on the other hand, is not function of theta. So when you differentiate it, this term will be 0. Vz is not function of z. If you take differentiation twice, it turns to be 0. Okay? And that's gravity. Gravity in this case is equal to minus g because our axis is pointing up and gravity is pointing down. So gravity is negative according to our direction. All right? So I will need some space here. Okay. On the left-hand side, you get 0. On the right-hand side, you get dP by dz, and I will change partial differentiation in total differentiation because pressure is now function of Z only. We found from equation of R component and zeta component that pressure is not function of R. Pressure is not function of zeta. Now pressure is function of Z only, so therefore we can convert partial differentiation to total differentiation. Okay? Second term would be mu over R. Again, Vc is a function of R only. I can convert this into differentiation, total differentiation. That would be R dVz by dr minus rho g. Okay? Now I'm going to bring pressure to the left-hand side. So I get dP by dz plus rho g equal to mu over R d by dr R dVz by dr. All right. Now you see that the equation that I got from the Navier-Stokes equation is not the same as what we did by shell balance. It is not the same at this moment. And it seems like the equation is complicated and quite difficult to solve. Right? It's no longer simple integration anymore because you have differentiation on both sides. That means now you have differential equation. So either you solve by using what you learned in GMAT, or you have to pay attention. You have 10 minutes left. So let's see how we can do it. Now you have to understand pressure is a function of Z. Okay? Velocity Vz is a function of R. The rest are constant. This is constant, constant, constant. Okay? So that means this side of equation is a function of Z only. On the right-hand side is a function of R only. Now you have to imagine one thing changing with respect to Z. How can this thing be equal to the other thing that changing with respect to R? Is that possible? Because Z and R are independent. Okay? So function of Z can never be equal to function of R. The only thing that makes this equation true is that both sides are constant. It's not function of R, it's not function of Z. Right? So you have to realize, although the pressure itself is function of C, it seems to be function of Z. Vc seems to be function of R. But the whole term here, after doing differentiation twice, the whole thing is supposed to be constant. Otherwise, this side and that side cannot be always equal. So the condition of this equation is that both sides must equal to constant. And you have to realize that on your own. Okay? And this technique cannot be done if this is not total differentiation. If it's still partial differentiation, then Vc is function of two variables. Then it might not be constant. Okay? So this can be done only when you convert into total differentiation only. Now, I'm going to split dp by dz plus rho g equal to constant. Let's say this one is C0. If you move everything to the right-hand side and integrate, you get P equal to Z times C0 minus rho GZ plus another constant C1. In order to find these two unknowns, you need two boundary conditions, right? So boundary condition would be at Z equal to 0, pressure is P0, and at Z equal to L, pressure is PL. These two should give you C0 and C1. Plug the first boundary in, plug the second boundary in, you get two equations, solve for C1 and Z0. You end up with C0 equal to modified pressure PL minus P0 over L. And C1 would equal to pressure 0. Okay? On the other side, if you take this equation, mu over r, d by dr, r dvz by dr equal to C0, which is already known. From that part, C0 is known number now. If you take this mu into the right-hand side, you get d r dvz by dr equal to C0 r over mu. All right? Integrate this one, you get r dvz by dr equal to r squared C0 over 2 mu plus C2. At this point, you can apply boundary condition right away. For instance, you can say that at r equal to lambda r, lambda times capital R, dvz by dr equal to 0. Then you can solve for C2. Okay? If you know C2, then you integrate it again, you get velocity profile. Or you can go ahead and integrate it right away. You end up with dvz by dr equal to r C0 over 2 mu plus C2 over r. Keep integrating it, you get vz equal to r squared C0 over 4 mu plus C2 logarithm of r and C3. C0 is known already, it is pressure. You need two boundaries to find C2 and C3. The boundary would be at inside wall, velocity is 0, and outside wall, velocity is 0 as well. So after that, you get the same velocity profile as what we did in chapter 2. All right? Any question? So sometimes when you use this set of equation of continuity and equation of motion or Navier-Stokes equation, sometimes you end up with the same equation or same exact way to do integration as what you do the shell balance. Sometimes you end up with some complicated equation that you need some kind of trick to solve. Okay? All right, if you have question, come and ask. Otherwise, on Tuesday, next Tuesday, I have to cancel class because I have to go abroad. So see you on next Thursday. The homework would be due on Thursday.